Thanks, Duncan, and thanks, Duncan and Julian, for the invitation. Um, I realized that the title is a bit of a giveaway. I would have rather phrased it as "Do all three manifolds bound definite four manifolds?" But that was a bit, it was a bit too late for that. So since everything is already in the title, I might as well start with giving you the statement of the theorem that I want to tell you something about. So the theorem that I proved with Kyle Larson somewhere towards the end of last year is that this person, which I will tell you something about in what follows. This is a three manifold. This is a three manifold, does not bound any definite four manifold. And I think that what I want to convince you of is, well, first of all, I want to tell you what the statement means. And in order to do that, at some point I need to tell you who this person is. And at some point, I guess I will need to tell you what a definite four manifold is. And I want to convince you that maybe it's an interesting statement and a statement that even people who do not do 3.5 dimensional topology might care about. So let me start by telling you what definite means. So I will take a bit of a long route around. So I will take it as an excuse to introduce one of the main objects of what we did, which is the intersection form of a four manifold. So if, let me call it W, is a four manifold, can be with boundary, without boundary, I do not particularly care, but I need an assumption. I need at the very least that W is orientable. Then I can take two homology classes and I can define their intersection product, which is the number of intersections between any two transverse representatives of A and B. So where A is the homology class of F, B is the homology class of G, F and G intersect transversely. This makes sense. Well, yeah, this is something that doesn't require a lot of structure in order to make sense. And the sharp sign here means that I'm counting intersections with signs. And exactly the sign is where I need the orientation of the four manifold in order for things to make sense. So Q of W, I will generally think of it as a bilinear form, which is even symmetric and integer valued. Not really on H lower 2 of W, but rather I want to mod out by torsion. And I will refer to anything with such a structure, so a free Z module, generally finitely generated of finite rank, but so far I didn't really use that with a symmetric bilinear integer valued form. I will call this a lattice. And I will say that W is negative definite if Q of W is negative definite. That is to say, if for all classes in this H2 mod torsion, except for the trivial class, we have that Q of W of A is strictly less than 0. And well, in an analogous way, I would say that Q of W is positive definite if, well, under the same assumptions, QW of AA is strictly positive. That is to say, I don't want any non-trivial embedded surface in my 4 manifold of non-negative or non-positive self-intersection, depending on the two cases. If I were in France, I would say positive or negative, because at least here in France, we say negative for non-positive, which I find a bit bizarre, but okay. Yeah, so this is our definition of negative definite for manifolds. And let me remark maybe that if W is compact and the boundary of W is a union of rational homology spheres, that is to say, if you want that the homology of the boundary of W, the first homology group of the boundary of W with rational coefficients is trivial, then negative definite is the same as being semi-definite. That is to say, I don't really need to worry about whether this inequality or this inequality is strict. I can think about the weaker inequalities if I want to. But if this assumption is not satisfied, then I need to worry about that a bit more. And well, of course, I forgot to say that I say that W is definite if it's either positive definite or negative definite. And okay, and now at this point, you might scratch your heads a bit and say, wait, I think that your statement is wrong, because if I give you a 3 manifold, at least a homology 3 sphere, you know, I always find a 4 manifold that is definite, or at least semi-definite in the other case, whose boundary is your given 3 manifold. And this manifold is a very silly one, which is if Y is a rational homology sphere, well, then Y times the half line is a perfectly nice 4 manifold whose boundary is Y, whose intersection form is pretty trivial. When I write Q of W equal to 0, I mean that the group is the 0 group and the intersection form is the 0 bilinear form. And by my definition, this is pretty negative definite and positive definite. So if I want the statement to make sense, I should at least add one condition, which is the condition of compactness. And well, spoiler alert, in order for this to sort of apply to the theorem, spoiler alert, this is actually a rational homology sphere. So indeed, this particular three manifold does bound a definite four manifold, which is just a product. We add compactness, well, then we have something to munch on. Okay. And let me, maybe I'll postpone a bit telling you who this person actually is. And let me tell you why one should care about such a statement, why one should be interested in asking questions along these lines, and what was known before us and where the statement comes from somehow. So I would argue that if you're a topologist, if you do any form of differential topology, you have to be sort of interested in questions along the lines of given a manifold, an n manifold. I don't need to stick to dimension 3. An n-dimensional manifold. Why, when is y the boundary of an n+1 dimensional manifold, or given x, maybe I'll call it z, an n+1 dimensional manifold, when does y embed in z? And well, the first one, well, both are very, very classical questions. And we have some answers, of course. And one answer is this page. So this theorem of Rochlin from the 50s that tells us that, in fact, every three manifold bounds a definite form, bounds a four manifold, which in fact we can choose to be compact. Compact. This statement can be shortened up by saying that omega 3, the three-dimensional cobordism group, is trivial. So, one natural question, sub-question or follow-up question is, well, now fix y, I have a class. I have the B of y. This is the class of four manifolds whose boundary is y, with boundary of x equal to y. And by Rochlin's theorem, this class is non-empty. And one thing that you can wonder is, well, what are the minimizer of some complexity function on four manifolds within this class? So given a complexity function on B of y, or rather on four manifolds, what are the minimizers of this complexity within B of y? And again, there's a long history of this question. For instance, you can look at handle decompositions of your four manifolds, and you can ask, what is the minimal number of one handles that you need, or the minimal numbers of two handles that you need, or the minimal number of three handles that you need in any handle decomposition. And if you start, or the minimal number of total handles, or what is the smallest fundamental group that you can find. So if you stick to one handles, so the complexity is the number of one handles. In fact, it turns out that the minimizer, well, the minimum is always 0. And this is in essence the Licorice-Wallace theorem. That translates into saying that roughly translates into saying that every 3 manifold has a surgery representation as surgery along a link in S3. As a corollary, well, of course, this implies that the fundamental group, or the size of the fundamental group, always minimizes at 1. So then you can go higher up and say, well, what about 2 handles? What about the rank of H2 of these 4 manifolds? And a lot of these questions, as far as I know, are completely open, except that maybe, well, in some cases, we know, for instance, in some cases, the minimum rank of H2 has to be strictly positive. So there are results along the lines. If you put more restrictions on your 4 manifold, well, you might get some obstructions. Another natural measure, so I will call the rank of H2, this is normally called B2 of X. This is the second Betti number. And, you can wonder, you can look at the intersection form, and the intersection form gives you roughly splitting into a positive definite part and a negative definite part. And the sizes or the ranks of these 2 parts are invariants related to the signature or the index of your 4 manifold. And you have 2 invariants that are B2 plus and B2 minus that are I think they're called the positive inertia and negative inertia of the intersection form Q of X. And you can ask, well, can we minimize these? That is to say, if you want to, so how can we minimize? B2 plus or B2 minus. And asking whether B2 plus or B2 minus is 0 is asking whether given 3 manifold bounds a negative definite or a positive definite to manifold. And if you minimize B2 plus times B2 minus, well, asking that the product is 0 is asking whether it's either positive definite or negative definite. And this first question has a long history. So this first question has a long history that dates back at the very least to Donaldson, who proved in 1981, perhaps, or 1982, that every closed orientable negative definite for manifold has a diagonalizable intersection. And now I'm really hoping that somebody asks a question. I can see, I don't see Duncan very well, but he seems too comfortable. And Donaldson's theorem has a very, has an assumption that is really, really crucial that I haven't spoken about yet. I was fishing for questions, but yeah.
I mean, I assumed you were working with smooth manifolds implicitly throughout.
Aha, you should never assume that. Well, I mean, knowing me, you can assume that, but yeah.
Well, you were talking about handles.
Yeah, I think you can have handle decompositions for topological for manifolds, and you can have transversality for surfaces in.
Okay.
Yeah, you disappoint me, Duncan.
Okay, fine.
So it has a crucial assumption that the four manifolds we're talking about are smooth. And by stark contrast, pretty much at the same time, Friedman proved that this is absolutely false in the topological category. So if we only have a topological for manifold, then the previous statement is false, and is false in a very, very strong way, in the sense that any lattice you want can be the intersection, and unimodular lattice is the intersection form of a closed topological form manifold. And there are plenty of definite lattices that are not diagonalizable. And well, now that I put the assumption in Donaldson's theorem, I need to be honest and add the assumption also here. Our theorem strongly needs the assumption that the four manifold is smooth. And in fact, what I can prove to you, well, I will not do it during the talk, but what I can prove to you is that indeed this three manifold does bound both a negative definite and a positive definite topological four manifold. There is a surgery for those in the loop. There is a surgery cobordism, just one single surgery, which is both one positive and one negative to an integer homology sphere, and then one applies Friedman's theorem. And this sort of closes the question quite quickly. So I don't know. I hope that I convinced you that this is sort of a natural question. You have a class of four manifolds, and you're asking for what are the minimizers of some complexity on this class. And I guess that up until very recently, it was not known whether one could achieve zero according to this weird form of complexity. What was known, actually using Donaldson's theorem, it was known that many three manifolds could not bound something positive definite or something negative definite, but mixing the two so far had seemed elusive. Let me name one example, the Poincare homology sphere. Which for me is the link, well, it's also sigma 235. This is the link of the complex surface singularity x squared plus y cubed plus z to the fifth equal to 0 in C3. I'm going to talk about this more a bit later. So this is an example of a three manifold that does not bound any positive definite three manifold. It does bound a negative definite one, which is the E8 manifold, which is the resolution or the Milnor fiber of this particular singularity. And I name it also because P is the same P that appears here. So this manifold, well, now we have half of it or 3/4 of it. So it's the connected sum of this weird object that I'm going to define very soon. And it's connected sum with 3 copies of the Poincare sphere with the opposite orientation. So I only need to tell you what this person is, and I will do it very, very shortly. So when I say that the answer to this question was not known until very recently, well, it's really very recently. Unfortunately, we're not the first to prove such a statement, but Nozaki, Sato, and Taniguchi in 2019 proved a similar statement, well, the same statement, with a slightly different manifold, which might have been something along the lines of sigma 2, 3, 12k plus 1 minus 2p. So the same shape, the same type of example in some way. But this is an integer homology sphere. Ours is only a rational homology sphere, but you know, this is, I would say, almost fine print in comparison to the difference in techniques used. They used filtered instanton Floer homology, which is something that I don't know a whole lot about, but I know that it's very different from what we do. And similar statements in one form or another had been proved by Freuschov in his PhD thesis with an extra assumption on torsion homology, but that's still unpublished as far as I know. So it should be somewhere in his thesis, but so let me say CF Freuschov. And yeah, so let me introduce what this person is at last, and then I'll pause a bit for questions before maybe sketching something about the proof. So who is this person? Well, this is a ciphered fibered space. I will give you a surgery representation. So you take this simple 4-component link, you do -2 surgery along this big component, -17/3 surgery about this component, -15/13 surgery on this one, and -23/22. If it doesn't tell you much, what it means is that I'm taking the complement of a neighborhood of this link. So I'm drilling out some neighborhoods of each component, and I'm gluing in solid tori so that the meridian disk wraps around the knot. Well, in this case, once in this direction and twice in the other. And in this case, 23 times in one direction and 22 in the other. If you want, there is a 4-dimensional description as the boundary of plumbing. If you're more complex, if you're more complex geometric oriented, what happens is that M, this person, is the boundary of, or the link, no, the boundary, it's fine, of a complex surface singularity. Which happens to be, I think, in C6 defined by 9 equation. By 9 equations. But the gist of the situation is that you have a complex surface. So a four manifold with a singularity. which lives in some Cn, and you take a sphere, well, a small sphere, round sphere, as 2n minus 1 of radius epsilon in Cn, centered at the singularity, and you take the intersection between your complex surface and this hypersurface in Cn. If you take epsilon small enough, this intersection will be transverse, and it will give you a 3-manifold, and this 3-manifold is what we call the boundary of the singularity. So there you can write down equations in C6, 9 equations that give you a surface, which is not going to be a complete intersection, but that's life. And the link of this singularity is going to be this 3-manifold here. And note that as a complex surface singularity, this implies that our M ... is automatically the boundary of a negative definite 4-manifold. Namely the resolution of the singularity. And note that P in the statement also I introduced you as the boundary, as the link of a singularity, and so it also bounds a negative definite 4-manifold. However, here we're doing an orientational reversal issue, so you cannot just take a boundary connected sum of these 4 manifolds and get something definite. You get something mixed every time you try to do that. So the statement is not obviously false. This is maybe what I wanted to convince you of. And I guess that maybe this is a good time to pause for questions before maybe telling you something about what goes into the proof without going into details. I only now realized that I slightly cheated. I also need oriented, but
could you remind me what the other example was of the, I guess it was a Japanese group?
Yeah.
Okay.
So it's arguably a lot simpler than our example, and it's a lot more satisfactory in many ways, in the sense that this is a statement about integer homology spheres. Whereas, well, if you do the computation, thanks for asking the question, it turns out that the first homology group of M ... is Z mod 2Z, which is very crucial. It's small, but it's not an integer homology sphere. And maybe I'll take the chance, since you've asked this question, to say that what they do, the techniques that they use, are not applicable to our manifolds, and vice versa, what we do is not applicable to their manifold. So what we can do, they can't do, at least not yet. Like, the technology is not there yet. I think it's just a matter of the technology not having been developed, but so far it's not accessible to them, and what they do is absolutely not accessible to us. Like, there is no way that we can tweak what we do to get to their examples.
So you see, yeah, so they've taken a connected sum with 2 negatively oriented copies of P. You do 3. If you add more on, will you still get the same conclusion?
Not that I know of. In neither of 2 cases do I know that. In fact, I think it's a cute question that I have no idea how to answer. If you give me a 3-manifold and you connected a bunch of Poincare spheres, do you always bound something, well, positive definite, I suppose? Or if you subtract a bunch of Poincare spheres, do you always bound something of the right definition? Like, there's one sign that is obvious from which direction you're going, and does that ever work? I have no idea. But yeah, I really wouldn't even know how to tackle the question somehow.
And going in the other direction, finding a prime example?
That you can always do, because there's a theorem of Livingston that tells you that every three manifold is rationally homology cobordant, or even integrally homology cobordant to an irreducible one. And the statement is invariant under rational homology cobordism. So you can use Livingston's statement to buy yourself an irreducible one. In fact, you can even do more. There's a theorem of Myers telling you that every three manifold is, I'm pretty sure, at least rationally homology cobordant to a hyperbolic one.
Mm-hmm.
So yeah,
I see.
it's just that I don't have any concrete example of something. I think that Livingston's proof is pretty constructive. You start from a surgery representation, you somehow destroy all separating spheres by infecting the curves going through these spheres and destroying these spheres. But I don't think that this would be pretty or.
Yeah, and I presume starting with the hyperbolic manifold and asking if you can go the other direction and then land on say your example is.
That I would have no idea of how to do.
Right.
I've been playing around a bit with hyperbolic, with computing correction terms of hyperbolic three manifolds. And yeah, it's really hard. We don't know a lot. Unless they are like surgeries on hyperbolic knots, then we know everything. Well, modular knowing enough about the knot, which
mm-hmm.
something we can do to some extent. But otherwise, it's wild. Like there are recent papers of Lin and Lipnowski that have some spectral condition that allows them to compute correction terms if they can find some. I don't know. They use some cunning techniques around the Selbert trace formula, and they play around a bit, and they can compute in some cases correction terms, but the examples that they have are few and far apart. And in general, we have no good ways of computing them. Okay, so maybe if I can take 5-10-ish minutes to sketch what we did. Thanks, Duncan. So how does one go about proving such a theorem? Well, one looks at what had been done in using, ideas that were initially Donaldson's perhaps, and then declined a bit further by Orschwart and Sabo, using Heegaard Floer to give obstructions. So the main tool is Orschwart, Heegaard Floer correction terms. Which are defined by Orschwart and Sabo. And have proved to be a really useful tool to obstruct negative definiteness or positive definiteness, but combining the two so far hadn't been done. And I'll be lying a bit, but correction terms are rational numbers associated to a second cohomology class of Y. So you have as many of them as you have second cohomology classes or first homology classes by Poincare duality. And they have nice properties in the sense that they are additive with respect to connected sums. and orientation reversal symmetric. And they also have a really nice, remarkable property with respect to negative definite compositors or positive definite compositors. So that, I guess that to a large extent, they were devised so that one could use them to obstruct the existence of compositors or to study such compositors. So what we prove with them is proposition or maybe theorem. If Y is a 3-manifold with H upper 2 isomorphic to Z mod 2, for instance, RP3, and Y is the boundary of a negative definite 4-manifold, then well, D of Y 0 plus D of Y in the class that is non-zero, which I will call 1 very imaginatively, then this quantity is non-negative. And moreover, if equality holds, then D of Y0 is either plus 1/4 or minus 1/4. Great. And I want to mention that in the course of the proof of the second statement, you need to classify all lattices L with determinant equal to 2. Determinant you can think of as the co-volume or the determinant of any Gram matrix for L, such that L plus L embeds in Z twice the rank of L with the standard Euclidean bilinear form. This is an embedding of quadratic forms or of lattices. So you want the bilinear product to be respected, or if you want this to be a sublattice where you restrict the Euclidean product.
What do you mean by classify? How explicit do you?
So by classify, I'm being vague. I can tell you the answer. The answer is that L has to be diagonal. Which is a bit of an analog of, if L were unimodular, this would be a silly statement, or not too silly, but it's like unique decomposition of positive definite unimodular lattices. So we're proving this indeterminate too somehow. Great. And then with a little bit of work, which is fairly standard, once you have this, then you know that the correction terms of Y are determined by L. Or by Q of W. And this essentially implies that they have to be the same. They have to be 1 plus or minus 1/4. Somehow this tells you that you're reducing to algebra, and then you compute things only algebraically. And this, how you get to here, this is using a theorem of LPs. Which characterizes unimodular lattices of a certain type. Great. So once we have this proposition, we need to get some computations done. So the rest of the proof is actually computation of D of our nice manifold 0 and D of our nice manifold 1. And these people turn out to be something like minus 31/4 and minus 17/4, which again are numbers that don't tell you anything. But when you connect some with the Poincare sphere, you correct these guys so that they become minus 7/4 and plus 7/4. And so you see that they satisfy our inequality. So if it were the boundary of a negative definite for a manifold, well, you have equality in this inequality. So the correction terms would have to be plus 1/4 and minus 1/4. And this is impossible. But then if you reverse the orientation, you can play the same game with positive definite, because this condition of having equality in this equation is symmetric with respect to orientation reversal. And so this buys you at the same time the negative definite and the positive definite case. And the work that goes into proving, into making some computation, well, we didn't really do it. We used a computer program by Chari Karakourt, who implemented an algorithm that dates back to Oshvat and Szabo, and then that was refined by Nemeti for computing correction terms of, I guess, links of singularities, links of surface singularities, or at the very least, cipher fibered, small cipher fibered spaces. And so the work that we put in was actually to go and hunt for a 3-manifold that gave us the right correction terms. So we had to compute a lot of examples and see and hope to get something out of it. So luckily this turned out to be possible.
So what happens if you, rather than using that particular Seifert manifold, you just looked at 2/q surgery on a knot in the 3-sphere? You mentioned before that, you know, you can, a lot of the calculation is known, at least theoretically.
I think that what happens in that case is that when you do 2/q surgery along a knot, the two correction terms can never be too far apart. Somehow, in order for this trick to work, you know, these could be as negative as we wanted. It could have been minus 2000 and minus 3000, but the important thing for the statement to work was that they are sufficiently far apart.
Mm-hmm.
And if you do surgery along a knot in S3, then you have a control on how far apart the two correction terms can be.
Not least if you do surgery on a knot in S3, then the resulting manifold bounds something definite.
Yeah, but then you can correct it back with, compensate with some copies of the Poincare sphere. So if you take a knot with very large negative, with very large V0, for example, and very large V1, then doing plus 2/q surgery gives you something with very negative correction term. And then you would compensate by subtracting a bunch of Poincare spheres. But you can never get the distance between the two sufficiently far for this trick to work. Yeah, I think I said what I wanted to say. So.
Okay, well, thank you.
Yeah.
I actually have a question.
Hi, Antonio.
Hey, ciao. So this is like, it's a Z2 homology sphere.
Yes.
But in the Eastonton paper where they use like the Chern-Simons filtration, like the one you mentioned before, in there, like they do integral spheres, right?
Yes.
So in this sense, the examples you found and those other examples are different. Yeah,
they are different. They are not rationally they cannot be rationally homology covariant. So you cannot say use one to show the other, at least not in an obvious way. And as I mentioned earlier, with replying to to Steve's question, their techniques so have not been yet developed for rational homology spheres. And if you try to play the same game with the integer homology spheres that we play, you don't have enough correction terms.
Yeah, that's what I wanted to say. So this argument for integral spheres, it's like fails, but their argument, I don't see. I mean, it's not cannot be adapted immediately because there is this problem that with the rational spheres, and so I think they are really different examples. I mean, I don't know.
So I wouldn't exclude that a year from now, somebody develops filtered instanton Floer homology for rational homology spheres, and they come up with other examples. Like
I have no doubt about that too. But at the moment, we can really say that it's sort of a different are different examples, and they are different technologies. Yeah, very interesting. Thanks for the nice talk.
Thanks, Antonio.
Yeah, so you said that if you're doing 2/q surgery on a knot in the 3 sphere, then somehow that forces these invariants, these d invariants to be close. But if you started rather with just a knot in a Z homology 3 sphere, is that also? I mean, it's not always. What does that do? Anything?
That is an interesting question. So there are two answers to the question. One answer is that our M is obtained as +2 surgery. Actually, let me call it sigma +2 k, and it's also sigma prime -2 of k prime. So for our specific M, you look at the plumbing. So you have this big plumbing presentation, which it's essentially the resolution of the corresponding singularity. And you can choose whichever vertex you want, whichever, not vertex, at least the leaves. You can choose either of the 3 leaves or even the central vertex. And you can find, you choose this one and you can find a negative number so that the whole thing is a Briscoe sphere. And you can find another one, which is like 2 away from it, for which this is a Briscoe sphere with the opposite orientation. So this tells you that M is at the same time a negative surgery, well, a positive surgery along, maybe I should put a minus here. I'm not sure about the minus actually, sorry. It's both a positive surgery and a negative surgery along some knot in some Briscoe sphere, perhaps up to orientation. And this is what I was mentioning earlier when I said that the theorem is very false in the topological category. Once you have such a surgery picture, well, that you can view at look at the trace of the cobordism and then glue in Friedmann's sphere and produce something negative definite or something positive definite whose boundary is your M. There's another question which I like perhaps even better, that any 3 manifold with H1 equals Z mod 2 is 2/q surgery or -2/q surgery along an integer homology sphere. You can even take it integral, actually. You can find an integer homology sphere and a knot inside it, such as doing -1, -2, or +2 surgery. You obtain you obtain back your initial 3 manifold. This is, and I don't know, it's cute to prove. You just take the generator of H1 and you know that there is a filling that kills the homology, and then you take, oh yeah, I got it. You need to worry a bit about which slope you pick, but you find one that such that the dual surgery is integral.
Yeah. So what's the generic, is this phenomenon of constructing such a manifold generic, sporadic? What do you think?
I want to say that there is absolutely no reason that if you give me a random 3 manifold, it bounds something definite. By experience, it's really, really hard to construct them. Like we had to sift through maybe 30 examples, maybe more, before we could find one that worked. But I mean, we're looking at the world of 3 manifolds through the eyes of Seifert. So we're looking at a really, really narrow part of all of 3 manifolds. So it could be an accident of, it could be a small numbers phenomenon. It could be a Seifert versus rest of the world phenomenon.
But how is the story? Like every manifold is cobordant to a hyperbolic one, right?
Yeah.
So, I mean, when you do this, like saying you can find a hyperbolic example, it's sort of...
Yeah,
so,
but,
I mean, yeah.
But you still find a hyperbolic example that is homology cobordant to a Seifert one. Like how many of
I
those
understand. I understand. So
my personal expectation, I have nothing to back it up, but I think that this should be a pretty generic phenomenon. But I really have no proof whatsoever. In fact, I have proof of the contrary, but you know, sweat and tears.
maybe to build some genuine hyperbolic examples, one can use some surgeries on connected sounds.
I have absolutely no idea. Like I tried and failed so far. The problem is that we're really bad at computing correction terms. Like we know how to do it for essentially maybe 2 classes of manifolds and maybe 3 classes of manifolds with overlaps. So it's not great. I can say that we're better at this than computing filtered instant on homology, but you know that's not much to brag about.
Okay, let's thank Marco again.